Let's begin with the first question. The magnitude of magnetic field produced by a straight current carrying wire at a given point is directly proportional to current passing in the wire and inversely proportional to distance of the point from the wire. See, whether it is true or false we need to find. Suppose let us consider that this is the current carrying wire. The magnetic field around it will be in the concentric circles like this. Okay. So the distance of the magnetic field lines is given like this. This is the distance. As the distance increases, the magnetic field strength is going to decrease. As we increase the current, what happens? The magnetic field strength is going to increase. So that is, the field strength will increase when the current is increasing, and field strength will decrease when the distance is increasing. So therefore inversely proportional they are. Okay, so this is right. So the distance is inversely proportional, whereas the current is directly proportional. Option A, true. The magnetic field lines around a straight conductor carrying current or concentric circles whose center dash. Option A, lie on the wire. Option B, lie out of the wire. Option A is correct, lie on the wire. See, this is the current carrying wire. So how the center is placed? Center is placed on the wire. Lie on the wire. Option A is correct. The center lies on the wire. The direction of the magnetic field produced by the straight wire carrying current can be obtained by using Fleming's left-hand rule, Maxwell's right-hand rule, Maxwell's left-hand rule, Fleming's right-hand rule. Fleming's left-hand rule is used to find the direction of the motion of the conductor in motor, whereas Maxwell's right-hand rule is used to find the direction of the magnetic flux when the current direction is known. And third one, Maxwell's left-hand thumb rule. We don't have such rule. And Fleming's right-hand rule. It's used for finding out the induced current in the generator. Finding out the direction of induced current. So option B is the correct answer. Right-hand thumb rule. Okay. If the thumb represents the direction of the current, then the remaining four fingers represents the direction of the magnetic field. Option B is the correct answer. Maxwell's right-hand thumb rule is also known as, say, suppose if we consider a screw, a corkscrew, and if we drive this corkscrew in the direction of the current, the direction of rotation will indicate the direction of magnetic field lines. So option A, Maxwell's corkscrew rule. Option B, Fleming's left-hand rule. Fleming's right-hand rule. Option C, option D, Maxwell's left-hand rule. No, it is also known as Maxwell's corkscrew rule. Option A is the correct answer. When electric current flows vertically upwards, the direction of the magnetic field produced is anti-clockwise. You know that? Suppose if the current is flowing like this, upward direction, then the magnetic field direction, how it will be? It will be anti-clockwise direction like this. It will be anti-clockwise direction like this. Use your right hand thumb rule. So it is very clearly seen. Okay, we can observe very clearly that the thumb indicates the direction of the current and remaining four fingers represent the direction of magnetic field. It is anti-clockwise. So option B is the correct answer. Similarly, when electric current flows vertically downwards, then the direction of the magnetic field will be. See, when the current is moving downwards, what happened? The direction of the magnetic field will be clockwise direction. So keep your right hand and your thumb pointing downwards. You will find that the remaining four fingers will be rotated in the clockwise direction. So option A is the correct answer. A magnetic field is produced when the current is passed through a straight wire. Yes. So when we pass the current through a straight wire, what has been produced? Magnetic field will be produced. That's true. Option A is the Correct answer. The magnetic field lines are circular near sound carrying loop, current carrying loop, light carrying loop. So it is current carrying loop. Just now we have seen. Option B is the correct answer. At the center of the circular loop, the magnetic field lines are. How are they? At the center of the circular loop, see here, when we take this is the circular loop, you think a circular loop, and we are passing the current. So the current goes like this and it comes, rotates, the current moves and it goes this way. So now here we will be having concentric circles on the edges, okay, whereas at the center of the circular loop it will be parallel like this. So this is the center of the circular loop. So at the center of the circular loop, the magnetic field lines are straight. Option E is the correct answer. In the above figure, the direction of the current in this phase of circular wire is. The direction of the current. So here they have given the pole. They have given the pole, it is south pole, and the direction is, see here, it's a clockwise. So option A is the correct answer, clockwise. The direction of the current in front of a face of circular wire is clockwise. Then the direction of the current in the back face of this circular wire will be. See, in front face if it is clockwise, then back face it is going to be anti-clockwise. Option B is the correct answer. Okay, I hope you are able to follow. See, suppose if we are passing the current through a wire like this. So here the current is clockwise. This end it is clockwise. And this side you will find that it is anti-clockwise. So clockwise direction south pole, anti-clockwise direction will be north pole. Okay. So this side it seems to be clockwise. Then the other side it will be seeming that it will be, this is clockwise means on the left side it is clockwise means right side it will be anti-clockwise direction. So option B is the correct answer. The solenoid is a long coil containing a large number of close turns of insulated copper wire. Is it true? Yes. So it is insulated copper wire wound like this in a cylindrical fashion. Okay, so option A, it's true. The magnetic field produced by a current carrying solenoid is similar to that of magnetic field produced by a bar magnet. Yes, of course. So when you find that what is the magnetic field around a solenoid? So when we draw the magnetic field around a solenoid and we observe that their magnetic field will resemble that of a bar magnet. Okay, that's true. The magnetic field lines inside the solenoid are in the form of. So inside the solenoid just now we saw that they are parallel straight lines. Option E is the correct answer. If a current carrying solenoid is suspended freely, it will come to rest pointing in which direction? North direction, east north direction, north south direction and south direction. See, when we suspend freely the bar magnet, when we suspend freely the bar magnet, it will align in north-south direction. The same way, okay? The same way, the solenoid will also align in north-south direction. Option C is the correct answer. Larger the number of turns in the solenoid, greater will be the magnetism produced. Yes. So the magnetism produced is directly proportional to the number of turns and directly proportional to current and inversely proportional to the distance. So as the number of turns is increasing, the magnetic field strength is also going to increase. Magnetism is also going to increase. So it's true. Option A is the correct answer. Larger the current passed through the solenoid, stronger will be the magnetic field produced. Yes, just now we have seen the expression. So magnetic field strength depends upon the number of turns and the current. So if the current is large, magnetic field strength will also be large. Option A is the correct answer. True. If we increase the number of turns in the coil, the strength of the electromagnet, number of turns if we increase, what happens to the strength of the electromagnet? Yes, it is going to increase because they are directly proportional. Just now we have seen. Alnico is an alloy of aluminium, nickel, cobalt and carbon, iron, nickel, cobalt and carbon, aluminium, nickel, cobalt and iron, tungsten, cobalt and carbon. Option C is the correct answer. Aluminium, nickel, cobalt and iron. Okay, Alnico. Name the type of material with which the magnetic field pattern of a current carrying solenoid resembles. The current carrying solenoid resembles, the magnetic field will resemble that of bar magnet. Just now we have seen. Yes, so this is the bar magnet, the magnetic field strength of this bar magnet as well as the solenoid, it's going to be same. See, it will be parallel and concentric circles. So north to south outside the bar magnet, north to south inside the bar magnet, south to north. So they resemble same. So it resembles like a bar magnet. Option D is the correct answer. Magnetic field around a current carrying wire is in the form of, just now we have seen, isn't it? The current carrying wire. So magnetic field around a current carrying wire is going to be in the form of concentric circles. Option is the correct answer. What is solenoid? Solenoid means, just now we have discussed, solenoid is a coil of large number of turns closely wound in the form of a cylinder. Let us see which option C is correct. A coil of small number of turns closely wound on a hollow sphere of conductive material. No. A coil of large number of turns closely wound on a hollow sphere of insulated material. No. A coil of large number of turns closely wound on a rectangular plate of insulated material. No. A coil of large number of turns closely wound on a hollow cylinder of insulated material. That's right. Option B is the correct answer. The strength of the magnetic field inside a long current carrying solenoid is. How it will be inside? See, this is a long solenoid, you think. Okay, long solenoid. So how will be the magnetic field strength inside? Outside the bar magnet is going to be like this. Inside the bar magnet is going to be parallel like this. So they are uniform, same at all points. More, let us see the option. Option A, more at the ends than at the center. No. Minimum in the middle. No. Same at all points. Yes. Found to increase from one end to another. No. Option C is the correct answer. Same at all points, uniform. In a straight current carrying conductor, what happens to the magnetic field when the direction of the current is reversed? When we reverse the direction of the magnetic field, then the magnetic field also get reversed. Okay, magnetic field direction will also get reversed. Magnetic field also get reversed in direction. That means, suppose if we connect like this, so we have this is the current carrying conductor. Now the current flows this way. So as the current is moving here, what happened? The current is moving upwards, so anti-clockwise direction. The direction of the magnetic field will be anti-clockwise direction. Now if you reverse the polarity, it will move in clockwise direction. So therefore the magnetic field strength is also getting reversed. Option A is the correct answer. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called core, valve, flux, solenoid. It is option D, solenoid. Hi viewers, I have discussed various objective type questions on magnetic field due to current carrying, straight conductor, circular loop and solenoid. If you like the video, kindly click the like button and subscribe my channel for the upcoming videos. Thank you.